Hey, how are you? Yeah.
Okay, so it's my pleasure to introduce our next speaker, Tonghai Yang from the University of Wisconsin, who will talk to us about CM points and Kudla Rapoport divisors on Shimura.
Thanks a lot. Thanks a lot for the invitation. It's great to be here. So today I'm going to talk about joint work with Bruinier and Howard. So a little bit of motivation about the original Gross-Zagier formula. Let me give a formulation. Suppose you have a scalar modular form, Caspar form, and a new form. And this n also give you a modular curve. Suppose you have imaginary quadratic field. So t is less than 0. And such as that, say, every p divided n split in k. Then you can have geometry have some kind of pairing. So what's the pairing you go? You can have, suppose you have ideal. Okay, you can produce CM points. Let's call them y of a. Belong to here. Either you can define by just by numbers, or just go by. Let me write here n equal to n bar because it's split. And you can rewrite this as equal to c of a. I hope I get it right. C of a inverse of a. So this is an Hilbert curve, and this is another Hilbert curve. We have cyclic isogeny of degree n. So this is the point actually defined over x0 of n. Actually, it's defined over q bar. If you like, you can define over q bar here. On the other hand, you also can, if you have this, you also have kind of geometric function. It's called geometric. Tau is equal to the Heck operator. You act on y. Let's say that OK. O is the ideal minus infinity. So this is in the Jacobians. And you take the q to the m. And you can check this is Caspar form. And valued in here. So suppose I have, this is a module also with 2. Suppose I have a G, I can produce a theta lifting. Sorry, I have to put it up a little bit. G, just you do the typical theta. This is series. Another one, you take a Peterson product. Okay. So this is also in J0 of n. And it's not very clear actually it's in Q bar because you have one integral. But it is somewhere in, have some constant times some unit bar. Okay, that's here. And you can consider this pairing of these G, so this is theorem, and what A. This is nice when you have a curve. You can always make trivialized. Just add this here. You have this is Leontet equal to some Rankin-Selberg L-function derivative of g theta of A and the center. So let me explain what's the a little bit on that side. So this is really just called geometric theta lifting is pairing with another CM point. I think that's a divisor, this is a point. And this is what's here is, if you have an A, whoops. I would think that A actually seems as a lattice. So I'll give you a Hermitian form, x and y of A equal to x, y bar, and norm of A. Okay, the Hermitian form. And you can check this guy, this is a lattice, and this is integral. And also it's self-dual. So this is a self-dual lattice. Okay, self-dual lattice of signature is clearly 1, 0, because this is positive definite. And you can produce a theta function. It's a scalarized, non-scalarized. So really just equal to x in A and q to the and this certainly is a modular form. This is modular form with 1. And this Rankin-Selberg L-function is your Rankin-Selberg L-function. Under this condition, you can prove this actually at the center is trivial, so you take the derivative, and the derivatives are equal to. So one of the ideas is try to generalize this to higher weight. So what will happen with the higher weight? The question will be, what about higher weight? Analytically, you can think a little bit easier. I can take like G equal to S of N. So gamma 0 n, for example, you don't even be that. May not be even uniform for me because I really think of the linearly, the linear stuff. Okay, and I will replace this ideal by a lattice. So it's also OK self-dual lattice. Hermitian lattice, or it's Hermitian lattice of signature. Sn is a Caspar form for this group. S stands the Caspar form. This is the weight. This is the group. Oh yeah, sorry. Let's put A here. Same. And 0. So again, it's totally positive. And you can again produce similar like this. You can produce a modular form, and this is always automorphic because it's positive definite. And the modular form is in. Oh, I want to be not here. I don't have n here. Sorry. I really actually take it today just very simple. I can only do the level is really the d, the imaginary quadratic field, and the chi d to the nth power. And this will be always n minus 1, also d chi d to n minus 1. Okay. And so I can certainly do the Rankin-Selberg. And just for this, I'll write once we have to normalized like this way. So AG of n, and this here is a R lambda. His equivalent called R lambda of n, and here's perhaps I would even put this doesn't really make not much there, really just a notation for that use. And this is the L function. I wonder whether this guy will be vanishing at this center will be negative center. In general, this may not be vanishing at the center. Let's just pretend it got vanishing at the center. What's the derivative? That's what I want to do. This first approximation. And to do that, so what's it? So this is the analytic side is pretty easy to say. And on the geometric side, and you need to replace x0m by something else. And this something else we want to do is on the Shimura operator or unitary type. So it will be some kind of Shimura type or unitary type. This is unitary and of signature m minus 1, 1. So what specifically I want it to be like somewhere like this. So I take this m minus 1, 1 is Kramer's Shimura unitary type here. And what I'm saying is just I want to be moduli space of abelian scheme of dimension n. And iota is the OK action on there, OK, same OK. And lambda is OK linear polarization, and also want to be principal polarization. And to make it work over this Z or OK, you need some kind of, this is where the condition comes from, this curvature condition is shift F is subshift of A, locally free, and sort of a certain signature condition of M minus 1. I will not put it there. Okay? And this one is, we know is over OK, is over OK, is a flat, regular. That's what I need. And you also can do M of 1, 0. This is easy one. This is just Hilbert curves. And CM Hilbert curves, because I want to take, again, OK. This actually is compact because only over C only just fundamental points. So what I will take is M is equal to M of 1, 0 cross M of M minus 1, 1. This is the first approximation. And this guy you can do a Pareto simplification. Typically, you have lots of them, and this one actually have a canonical one. So I just compactify it. Let's have it compactified like this. Okay. So that's what perhaps we should use this one. And so where to get this, where to get the theta is a little bit more complicated. Here we do is basically replace the Hecke operator by this Kudla Rapoport divisors. So what you do is you have A0, have A, so I ignore this other data there in M. And you can look at the linear C here is equal to home. There's OK modules. There's something. Okay. So like this. And so this certainly is the OK module, just the OK module. And I want to be defined as some kind of Hermitian form, somehow related to that guy there. So Hermitian form will take like this. F1, F2, and I want to do like really like this. So start with F2, you have A to A dual, lambda. And then you have, what do I have? Oh, no, this is wrong. A0 to A, F2. Then you go lambda to A dual. And then take F1 dual to A0 dual, and you come back to A0. You take lambda 0 inverse because it's isomorphism. Okay. So you get a map from here to here. And everything is OK linear. So this is what's OK linear. If it's OK linear, it's going to have to be defined over OK. So this guy defined over OK. You can check this is positive definite. So typically we write like Z of if the M in Z, then M, I also put an OK here because I need a little bit more later on. And this is just equal to just A0, A, and you add a J there. J is in L of A0, A such that J is equal to N. So typical extra condition. And this basically cuts you to a divisor because it's just one dimension lower. And so here's the problem. The problem is this is even over C, it's a divisor, but how do you know it's a commutative trivial? And typically it's not commutative trivial. How you make it a commutative trivial, we don't know how to do that either. So if we to do neuron-Tate pairing on above, you need a commutative trivial. And we cannot do it. So instead we do integral structure, you need to do get a green function. So later on I will define green function. Oops. Phi of M, it was OK for, actually it's not just this, is C, but here is only defined over M, you need to do simplification. And turns out I need to do a little bit more like this. So I will put total here range is equal to Cm, OK. And you have to put a Zariski closure to M star, then you need to add some boundary part. I will not mention that just to say I have this stuff. So suppose you have this will be done later on. You hope to get, so you get Z hat of M, OK. Just this is my integral divisor, and this is green function, and you put this together. And you hope this will be a classical form. Usually is not. And so you also perhaps try to add something more. And then you hope this is a modular form. And so this is let's call them arithmetic of tau. So conjecture will be is a modular form. Okay, the modular form when you add in this ring is module. So we don't know that. So suppose you know it, and you can do the same trick as before. You can do theta lifting, suppose true. You can talk about equal to, this will be, this weight will be worth 9 n for gamma 0 n d and character chi d to the n. Peterson product, and you'll be again this is in. So this replaces the nice classical form by the modular form by the way down here. So this is the one thing I can hope it will be working. And if we do this, definitely it works. Okay. And second thing where you have on the curve, the divisor and the points are the same. Because they're both code dimension 1. And in general, if you want this M is dimension n over C. That's over Q of n plus, no, over C is n minus 1. So over OK is n. And here is n minus 1. The other one, you don't want to be a divisor again. You want to be codimension n minus 1. So I want to be a cycles, code cycles. I want to be what we call a CM cycle in actually in n minus 1 of m star. Okay, this. There is one simple way to construct it. You just take the m equal to m1, 0. This is compact. This is also compact. This is also compact. This is just and this also mapped to m star. Just do like this: a0, a1, a, b equal to a0, a1, b. And only thing is that the extra shift f will be just equal to the algebra of b. Because that's a sub shift here. Okay? And this is dimension 0. So it's codimension n minus 1. And if I have a lambda, remember, so you can produce lambda just equal to all this guy here, a0, a1, b, such that home a0, b equal to lambda. Okay. So pretty much define everything. I think I wanted to compute this. Compute theta arithmetic group of y lambda. This is the pairing. I hope this can be equal to C derivative of f center. Okay. And this makes sense. You just go like this. You take this and you map to this. You put it here. So this is this is just one dimensional. You take a degree. This is what I mean here. I have a cycle here and put back to here and take a degree. This is what I want to do. And this is the first approximation of our theorem. And first, this side I have to change because this is not, in general, is not 0. Second, I don't even know this guy is modular. Right? I cannot just assume a conjecture. That's not very fun. So the whole talk is about to modify both sides to make it actually work. So to do that, actually, we will first we replace the G by something more general called harmonic mass form, and also scalar become vector valued. So actually, everything M also have to be cut off. Everything is too big, cut off the pieces. So I want to give the input gadget have 3 input gadget. go one by one. First one is basically just a lattice, but it's easier to more convenient to say is a kind of L. It really is two parts, finite part and infinite part. And this Hermitian form is called incoherent OK hat, that's this part, and K infinity, that's really just a self-dual Hermitian form, Hermitian lattice module of signature and 0. Okay. So what this really is just so let me just i.e. conclude it like this. LF is just a OK self-dual Hermitian module. And I think its self is already known, but let's just make sure it's true. The invariant of L of P, so this really is equal to tens of LP. P is less than infinity. This is equal to 1 for almost or P. I think this can be proved, but I haven't thought last night. Let's just keep it there. And L infinity is just the Hermitian space. K infinity space of signature and 0. Okay. So I explained this part. And the incoherent mean, the incoherent just mean you take the product of invariant of P. P is less than infinity, including infinity is equal to -1 instead of positive. Okay, positive. No, it's Q, because I think it's a Q. If you have a P split, if you think it should be a two copy of Q together instead of not just one. It's P. Yeah, module over K, but the Hermitian form is also K, but it's Q prime indexed, right? But otherwise, you split what you do. Yeah, K is quadratic extension, always the beginning. K is quadratic extension of, imaginary quadratic extension of Q. And eventually we'll assume this D is odd. But give a talk is, okay, this is what it really is more, so for example, if you, this actually is the same thing as exists OK self-dual lattice, Hermitian lattice, L of signature n minus 1, such that the L of F, that just means L tensor with Z, Z hat is isomorphic to L of F. And of course, L infinity didn't match up. One is switches there, you change the sign. That's it. Okay. And everything is come from there too. But this is easier because I can, here the L code we have the L could have a same genus, which L you pick is not really matter. So this is sort of nice. Also, when you do locally other part, you can watch that too. So this is the gadget. So how you do these things is a cutoff. I don't need the whole M. So what I need is here's the proposition. And if you give so K, they have too many K. algebraic closed. If you have A0, A is in M of F, then there exists a unique incoherent or O hat K infinity self-dual like this, such that let's call them L of A0 A, such that this L of A0 A of L is isomorphic to home of OK L and TL of A0. This is the theta module TL of A this for L not equal to characteristic of F. Okay. So by this proposition, you can figure out as M, you can cut into pieces. So all this A0A is geometric points come from here. Like this, okay? And of course, you can take star, you put a star here. So this is what I really want to do, is this one. This is the space I want to do. And also this is ZM, OK, is also you can cut to Z of L of M of OK. And I also need a technical, I need more. I really want to be all this cosets, I cannot do that. Actually, I want to be all this ideal. And this is K, this is a differential. I can define similarly Z of M of R and also Z of L of MR. Just a little bit technical condition, put extra there, okay? Not define that. So this is divisor. That's the first thing. Second thing I want to define is from this L, I also want to have something else is come from on, is called a wave representation. So take the L, and you also can produce L prime. L prime equal to all this X in if in general it doesn't. In general, but if it's a super singular, this is just at the P is changed. So if this is FP, this is equal to P equal to this guy here, characteristic P. When these both are super singular, then this one you can take, because this word is similar as home of L, this L0 and A, right? And so this really just, everywhere is the same except at L, at P. The P, originally you have to use to the module here, I just switched that to a self-dual. That's another reason why you have L, the script L here as an index instead of, this original, this somewhere I mentioned that before, but you need to keep changing different. Here, only each prime only changes once. This is called a neighboring lattice. Q hat and X. So you have what? X and X infinity. The infinity is just there. So the L, F. You take the trace, is in Z hat. And you also, of course, tensor is L infinity, didn't do anything, it's good. And you can talk about, so here's this is L prime of L is a finite Q of L, finite module with quadratic form Q of X equal to x and x in Q mod Z. Because if the Z hat here, Q hat mod Z hat the same as Q mod Z. Okay? And you can produce a wave representation omega equal to omega L. And then we started really, I want to really start not just the modular form, I really want to start modular form with this S of L. I don't have time, so I'm just define this stupid way. This way. And this is what I really want to do is here. But I told you this is not very cool because I don't know arithmetic theta. And so map it, there is something called, yesterday, the speaker mentioned, Vyazovska mentioned this modular form of, we call homomorphic modular form. This guy here is his row or row bar. Actually, there in middle, there is a more interesting one called harmonic Morse forms. This is the bar, and there's a Cauchy operator. This operator is pretty simple, actually. This is one of the differential operators I can understand. You just take a partial tau bar, and you take a bar again. This is a C bar linear. And this turned out to be exact. And what I'm really taking is, I want to take something here. So this is the second input. Second input is on this modular form. And this harmonic mass form will have a very nice property, always can split into two parts. The holomorphic part, and this is a holomorphic, but it's not a modular form, and this is not a holomorphic, but exponential decay. Okay. And really want to, in the end, I really don't care about this guy, I really care about Cauchy F. Cauchy F is the cusp form, really, I want to care about it. But this is just the thing I have to deal with. And this also looks like this. C plus of, let me also, even better, for this special case, further assume F is in this H2 mod N omega L of the automorphism of L prime L and this. This is the quadratic space, you take automorphism, silent group. And in this case, you can find out, it's very interesting, is this guy here can always write it as sigma of C plus of M R and Q of M. M is part in Q, and M is could have a negative term, but this like this, and phi of R. This phi of R is a characteristic function of R inverse of L prime L, right here, mod L. So you copy this right here. So this is the thing here. So the second one I wanted to find the divisor is so once you have that, you have a defined Z of F is equal to M bigger than 0, C plus of M of R.
Sorry,
Yeah.
Can please raise the
Oh, sorry, here, this. Wrong way. Just give me a minute. M of R. I forgot it was the L. The L is always there, so now L is always there, just forget about that part. So this would be Z1 of M here. We have to define the, I can put it here. Put a star here we want, but at this moment I don't want it right now. So how do you get green function for these guys? This is important. Really, I want to get green function with this. Let's first get green function with this. So green function comes from, as did yesterday, you just does theta lifting. So what you do is you have an L, and you have, so you also produce a theta of L. Yeah.
You mean C plus minus M? Otherwise, it's anything.
This one here?
Yeah.
Oh, I also have R there, so R. And this is differential ideal there. Which one, because I say it's defined, which ideal I can define that. Okay. I didn't define the R, but I just tell you, you could. And so as I'm like this, how do you define?
Yeah, you want negative for
Oh, that's definitely a bit too much. Like this, minus. Otherwise, it'd be infinity. So you can also define Z equal theta function. They have two variable theta of tau and have a Z. And depends on L, so it depends on L. This is the weight. Weight n minus 2 on tau. On Z, Z is on the, so Z is on the M. It is on M. And it's just function on MC. Again, the M really means this guy here. Okay? So again, you can do like regular theta lifting. What you do, you take this L of Z of F equal to F of tau and theta of L of tau Z. Oh, this is the value in SL dual. And the representation is dual representation. And this is on SL, this is on the SL dual, so you have in product, and the weight just exactly opposite to each other. So really just a simple one like this. And this is regularized because this guy have pores at the a negative pores. Okay. And it works. And the same calculation as basically the same calculation as you did with the weakly holomorphic, everything works. So here's the theorem. And basically due to over M, basically due to Bruinier and Funka, but here we do, let me put it in the cases. So the interesting case is ZF is actually well defined everywhere. Everywhere on MC and extend to boundary with log pores. Second, actually this guy is smooth away from ZF and boundary. Here, just say this actually, even though for the on the ZF, this guy is well defined, just not smooth. Okay. 3, and this is a green function of zeta accord total of f. What that really means is just you take z of f, you do Zariski closure, but that's not enough because you just define function why they match up, but not totally match up, and you need to add some boundary. And this is all explicit, so it works. So here's why we defined z hat of f equal to zf and phi f is in z1 of m star. Of course, then you can think it's L1 m star, okay, like this. And this is a small fact. If you give m, let's say give m, you can r, you can produce f of mr. This is in H2 mass n, L of this automorphism such that a divisor of f mr is equal to z of mr. Again, you put a total here, just you do a little bit modification. And it's unique if the n original n is bigger than 2. If not, it's equal to a little bit of trouble there, but you can fix it. Okay, so you can do that. So now I can really define the theta arithmetic of tau equal to theta total hat, here like this, and r q of m phi of r. Let's just r leave it away. You can put it here, the r there. Let's just okay. This is what I want to do, original one. Like this, and I want to say this can be try to exist something here to make it work. Such that this guy is a modular form. This is a weight n, blah blah blah. I don't need this for this talk, so just stick with this one here. So I have given you 2 input. One input is the script L. Second is the modular harmonic mass forms. From that produce arithmetic divisor. Okay, honestly divisor. No cheating there. And so third one is to produce same points. The same points what I produce is need third data, third input. So let me erase this here. Remember, I still need some positive lattice, the honest lattice there. So let me produce the third data is that. Third input is I can decompose the L so I can decompose. If it doesn't, which doesn't work, so equal to 2 parts. One is this. So what does supposed to mean? Let me first, this is an honest, okay, self-dual Hermitian lattice of signature and 1, 0. And this is incoherent type of 0, 1. Okay. Oh, 1, 0, so also 1, 0. So What do you mean this is? Well, this is a module, Hermitian module. And this is the Hermitian module. This is the Hermitian module of OK module. But if you tensor with the OK hat, it will automatically become a OK hat module. And infinity, of course, you just do the infinity. And this is what I mean by this. Okay? This is what I read. I need an honest one here. What's this guy giving me? Well, they give me two things. First, they give me cycle. Is y of dependent, this lambda, dependent L0, was equal to just equal to the modular space of A0, A1, B. Remember like this is in 1, 0, 0, 1, and 1, n minus 1, 0. Such that, so one condition here to cut it off. The first cutoff is I said before, the home of OK of A0B is isomorphic to lambda. So this is the honest lattice. Second one is the L of A0, A1. This guy don't have a home because this is action as the OK action, this is OK conjugate action. But you can this guy here, this is what I told before, this is L0. Okay, like this. And this is certainly the same cycle. And so the first thing I give you, second thing I give you is the theta series. Theta series. This will be a modular form, really honest modular form of n minus 1 omega this, and you take 2. It's always in the 2 space. Okay, like this. And third thing I can also give you is this guy is 1, 0. These are incoherent. And this is done long time ago, first started by Kudla. The L0, it also give you a incoherent Einstein series. So it's called E of tau dependent L0 S. And this incoherent Einstein series is cool, is always 0 when S equals 0. Okay? So therefore it is this. Now we're almost done. Because I produce 3 of them, I can produce Rankin-Selberg, and I can produce the Rankin-Selberg of, because C of F, and this is what I really want to do. This is my L function. This is a holomorphic Caspar form. This is a holomorphic modular form. You do Rankin-Selberg. This is equal to the C of F, take the bar, and take a theta, and take E. And then this is the weight n. This is the weight n with n minus 1, weight 1. So this is v to the n. And this Ernst Peterson product. And if you compute them, it becomes really Rankin-Selberg equal to something like this. This is A of m. And this will be all this stuff. This is the R lambda of n. But this will be, this is in S of L. This is in S of this 2. And this become A m to the S over 2 plus n minus 1. Not really important here. I have a gamma here. This is what we wrote before. So really like a Rankin-Selberg, if you compute them, just unfold it. That's all. And this guy here also is 0 when S equals 0, because this guy is vanishing at S equals 0. So automatic. So here's the theorem. Says, or what we defined is and y of this, right? This is a zero cycle here, and you take the inner part equal to negative degree of n y c, this is degree, but here times, this is what I need, negative derivative of c f theta 0. And actually, that's what I wanted. There are extra things that we also use for that on. This is a of plus m is 0, 0. Remember this, oh, not called 0, called OK. And times, here are some constant I don't remember, and the height of the curve. E is a CM curve. Okay, so this is the theorem we proved. And solved about 5 minutes. Let me give you some basic idea how you do it. And so first step is the same thing as she explained, just the same value. You compute the same value. So step 1. Usually compute the same value, just plug in of y. Y is this part. You do the same, this is the first computed by Schoeffer. We just do the same method, just compute everything. Then instead of KCF is 0, it's not 0. What you get is equal to this, equal to derivative of KCF and theta 0. And this degree is here. And so this part is new, and this part is already known before. It's a constant term of, you take the F automorphic part, you take a C here, and you take the derivative of this Einstein series derivative, and you plug into 0. But this is too bad, so you take the holomorphic part. Okay, that's it. And this is more like AP log AP, and this is my derivative. So what I want to do is just guess, well, the finest intersection is this part. The problem is step 1. Step 2 is try to compute other part. The problem is, so here's the problem, is the ZF, ZMR intersect with this Y of this here improperly. Let's make the whole work much, much more work than we wanted. That's what makes it more interesting. And otherwise, I just compute them and you're done. But the proper part actually can compute. In the way the proper part can compute. But the problem is this guy is not proper. Okay, so the idea is somewhere I defined there to have T hat. I never mentioned what's that. That's like a co-topological bundle with some metric. Is you try to move. So how you move it? You exist some number CF such that, and let me put it here. This is more such serious stuff. No. So to compute the improper intersection, we have to move away from it. Oops. So here's a theorem, technical theorem, says that exists some CF, some number, and a section sigma into Z of F tensor with T of negative CF. So now we use these both as 9 boundaries. This is originally divisor, but divisor can take as 9 boundary, such that first the divisor of these, you have a section, rational section, a divisor on these, may be complicated, but you restrict to this, it's not complicated. Put back to here is exactly equal to the proper intersection of Z, F, and Y. First part. Second part is we plug in, actually unical log plug-in log of sigma. You plug in this guy here, and you plug in any points Y square is equal to phi of Z of F for Z in Y of C. In other words, this guy here actually is useful. Even though originally you cannot use that, you can still do it because you can shift it. So what that means is this. Instead of doing like this, you can do Z of F Y. Now you can know what other thing equal to Z divisor of sigma Y plus T hat of CF Y. Right? Because this really equal to this tensor with this one. So it's linear. And this part we know how to compute because the intersection really is just a proper intersection we know how to compute. And plug in the value, and we just plug in the value there. So basically you got this guy is pretty much done. You just look at that guy there, you cancel everything, you really become like lactive and degree times F CF 0 plus some kind of the constant there, we don't know what to do, C0, 0, and some kind of constant here. So let me write here. Some star here, not important. So what's this guy here? Right? What's this? And these things are also very nice. This is like a line bundle. So you really just look at CF, can take it out. And so you really look at the line bundle on this. So the degree on this here. Okay? And each point here really just a kind of semi-equal curve. And this line bundle really moved to here, really just the Hodge bundle on the here with a shift. So you really just Kudla-Selberg formula. That's why the scissors showed up with this height pairing, height of E, times something, remember that. But the idea is clear, so it's shifted there. So this is the main idea. And as a corollary, we leave this. So you have the corollary, we have the theta, remember we have theta. This we hope this guy's a modular form. And we don't know how to do it, but we know this is the modular form. This really is the modular form on, honest the modular form on n and gamma 0 d and chi d to the n. Okay. And from these things here we did. I think I just stop here. Thanks. Oh, because you can compute. So ZF is just special case, right? For each one of these, you can compute them. You just compute everything there. You can just write, because what's this here? What's this here is like a Z of M. This, right? This range is equal to Z of, I didn't write them down, this is total F of MR. We know what is compute equal to. Which you can compute them. And the T also, we know how to compute that too. Okay, yeah. So you can compute everything.
But there's a formula for the pairing of T hat with itself.
No, you don't need T hat for itself. You T hat with Y is what you need.
Okay.
You don't need T hat to itself. That's complicated. And well, actually, yeah, T Y, we know that.
Any other questions? Okay, if not, let's thank Tonghai again. And we resume at 4:30.
Yeah.
So you gave this talk at Caltech,
yeah.
And you have this conjecture.
Yeah.
So this is basically a theorem, a case of this conjecture for this replace with this Y.
Where are we? Oh, we already know. I think we already know how to prove this. This is not a conjecture. It's just a theorem.
Oh, that's a theorem.
The theorem. No, this is a theorem. Oh. If I write very general, it's not true. This is only for very special. This is for the lattice self-dual. In general, we don't even know how to define them. So. No, this is theorem for this case. We know how to prove them. So. Yeah. Perhaps I didn't say it very clear at that time. So this is actually the theorem. The only problem there is for general, if I didn't define it just a space. Then you have a problem with the modular space didn't work. This is a typical problem with the geometry, arithmetic. How you do with the level.
So if you just